Hi, I'm Emanuele and I'm going to talk about TaDA Live, joint work with Julian Sutherland, Azadeh Farzan, and Philippa Gardner. TaDA Live is a new program logic that is able to compositionally verify total correctness of fine-grained concurrent programs with blocking behavior under fair scheduling. By total correctness here we mean that you not only prove safety of a program, but also its termination. To see why this is difficult, consider these two threads. They share a memory address X, and the thread on the right keeps on reading from X, waiting for the thread on the left to set it to 1, implementing a sort of signal between the two threads. This busy waiting pattern here is very common in fine-grained concurrency. We would like to prove termination of this program compositionally, which means, for example, that we want to be able to prove each thread in isolation, compose the proofs into the proof of the whole program. Moreover, we would like to be able to focus on a code fragment, analyze it, and produce a specification that can be used in the larger proof context. This is especially important if we want to have a modular system, because this could be the implementation of a library call, and we don't want to expose implementation details to the client, but just exactly the information needed to conclude the properties of the client that we are after. A well-known specification format for proving termination is total Hort triples. They assert that a program starting from a state satisfying the precondition will always terminate in a state satisfying the postcondition. For loops like this, this is not expressive enough. Of course, we can prove that the loop will terminate if x is always 1, but this is exactly the situation where this code is completely pointless. What we want to prove is properties of the code when x is shared and may change its contents. However, in such circumstance, the loop cannot promise to always terminate. The loop can promise to terminate if the environment sets x to 1 eventually. So what we need is a notion of termination conditional on liveness properties of the environment. TaDA Live's starting observation is exactly this, that blocking can be characterized by termination conditional on what we call liveness invariants. These liveness invariants conceptually encode temporal properties of the form always eventually a good state is reached. To turn these ideas into an expressive concurrent separation logic, TaDA Live introduces 3 key innovations. First, a thread, local, and resource-based way to reason with liveness invariants, which we dubbed subjective obligations. Second, a compositional way of reasoning about deadlock freedom, called obligation layers. Third, logical atomicity specifications for blocking code, which are the fundamental building block enabling modularity in the logic. I hope this brief introduction made you curious to know more about TaDA Live, and if so, come to the talk. Thanks for listening.